Hello, my name is Walter Maru. I'm a senior teaching assistant applicant for the 2025 PPCR course, and today we'll talk a little bit about correlations. The basic purpose of correlations is to describe the association between two variables. It's used for continuous data. It's important that both variables must be continuous. The association between variables is based on the study of covariance and can be positive or negative. The best visual way to analyze these relationships or associations are with the use of scatter plots, as you can see in the diagram on the slide. Correlation coefficients will describe the strength of the association between variables. We will talk a little bit more about scatter plots and correlation coefficients in the next slides. Let's start with scatter plots. Remember we said we have two continuous variables? Well, we plot one variable on the x-axis and the other variable on the y-axis, and we have this scatter plot. For example, in here you have a perfect positive correlation with a correlation coefficient of 1. We'll talk a little bit more about correlation coefficients afterwards, so don't mind these numbers right now. Here we see another scatter plot, but this time with a negative perfect correlation or a perfect negative correlation. Now we see a scatter plot with a strong positive correlation. And now another scatter plot, which is also considered a scatter plot of a strong positive correlation. Not as strong as the last one, but it's also strong. You can see there's a clear direction in between the two variables. Now we see a scatter plot with a moderate to fair negative correlation. And this last one is a scatter plot with a poor or no correlation at all. In this scatter plot, you don't see any direction of where the covariance of the variables are going. So now, we'll talk a little bit about correlation coefficients. They are represented by a lowercase r. It quantitatively describes the strength and the direction of a relationship between two continuous variables. The values of the correlation coefficient are related to the strength, while the positive and negative sign are related to the direction. The correlation coefficient can take values from -1 to 1, where a value of 0 means there is no relationship between the variables. As I told you in the scatter plots before, the correlation coefficients are the numbers that are within the scatter plot. So here, when you see a perfect positive correlation, you'll have a correlation coefficient of +1. 1 is the strength of the correlation. Remember, the values went from -1 to 1, -1 for a perfect negative correlation, and 1 for a perfect positive correlation, while 0 means no correlation at all. So here in the second scatter plot, or scatter plot B, you can see a perfect negative correlation with a correlation coefficient of -1. The only difference between the first and the second one is the sign. Then at scatter plot C, you see a correlation with a correlation coefficient of 0.98, which is considered a strong correlation. The same as scatter plot D, where the correlation coefficient is 0.78, also considered a strong correlation. In this case, as scatter plot C and scatter plot D are both positive, strong correlations, the sign is a positive sign, not a negative one. But now you can see in scatter plot B that there's a negative correlation, meaning that when the value of one variable increases, the value of the next one decreases. So here you see that the sign of the correlation is a negative sign. You have a minus sign. And you see that the correlation coefficient is 70, which means it's a moderate correlation, fair to moderate correlation. And in scatter plot F, you see a correlation coefficient of 0.14, which means there's a poor or no correlation, and you cannot see a direction between of the covariance between these two variables. There's a rule of thumb for the correlation coefficient, and you can see it over here. When you have a correlation coefficient of less than 0.25, it means that there's a poor or no correlation at all. When the correlation coefficient goes from 0.25 to 0.50, it means you have a low or to fair correlation. When the correlation coefficient goes from 0.5 to 0.75, it means that you have a moderate to good correlation. And when the correlation coefficient is above 0.75, it means that you have a strong correlation between the variables. But remember that correlation does not mean causation at all. Here in this diagram, you can see a nearly perfect positive correlation with a correlation coefficient of 0.99. But you can see that when you examine the variables, one variable is margarine consumption per capita and the other variable is divorce rate in Maine. So this correlation assumes that the more margarine you consume, the higher the divorce rates will be in the state of Maine, which makes no sense at all. So it's important that you understand that correlation is an association between the variable, but they have not a causal relationship or not a causal effect at all. There are some assumptions for correlation. The first one is that data must be continuous. Second one is that each subject must contribute to a score of X and to a score of Y. You have a normality assumption when you use the Pearson coefficient, but not when you use the Spearman one, which is the non-parametric counterpart of Pearson's. And it's important that X and Y are independent measures, so that one score is not a component of the other. For example, if one variable of us is velocity and the other variable we're trying to correlate is distance, it makes no sense because distance is a component of velocity, because velocity is described as distance over time. Now we'll talk a little bit more about the Pearson product moment correlation coefficient. It was developed by English statistician Carl Pearson, and it's the famous R-statistic correlation coefficient we've seen in the slides. It's used only for parametric data. And here's the formula. As you see, the formula seems a little bit complicated, but the only thing I want you to understand from this formula is that the Pearson product moment correlation coefficient uses the distances between the actual score and not the distances between the ranks, because in this type of correlation coefficient you are using the actual scores and not the ranks, as Spearman does, as you will see in the next slides. One important question: can the Pearson product moment correlation coefficient be subjected to hypothesis testing? Yes, it can. But it only determines if the observed correlation is statistically significant, which means that a p-value of less than 0.05 will reject the null hypothesis, assuming your correlation is different from 0. And this states that the two continuous variables are not correlated by chance. That's the only thing that a p-value or hypothesis testing does to correlation coefficients, but it has nothing to do with causation or with the strength of the correlation. Now we'll talk a little bit about the Spearman rank correlation coefficient. It's a non-parametric counterpart of the Pearson product moment correlation coefficient. The difference is that Spearman ranks the covariances, and it uses the rank differences instead of using the actual scores, as most non-parametric tests does. So here's the formula. It's not yet to see or understand, just for you to see that there is a D component in this formula, which is the distance between the ranks, not the actual scores. The Spearman rank correlation coefficient uses the RS, or the Spearman row statistic, and it can also be subject to hypothesis testing as the Pearson product moment correlation coefficient does. Well, thank you so much. Hope you liked this video. See you on the workshop. Bye bye.